So in the last class, we had looked into binary comparators, right? Where we had concepts explained on 2 bits, okay, 0, 0, 0, 1, 1, 0, 1, 1. So here we have 3 combinations equal to, greater than, and lesser than. So whichever condition is satisfied, that goes high, okay? Here in this case, it is 1, 1, so it's equal. Here it's 0, 0, it's equal. Here B has a value, high value, so which means A is less than B, right? So we developed equations based on these. Once we have the equations, it's easy for us to develop a logical circuitry. Similarly, when we increase the number of inputs, okay, to A1, A0, B1, B0, okay, so which means I will have combinations from 4 zeros to 4 ones. And accordingly, I will fill in this truth table. How do I fill in? I consider this as my A, consider this as my total B. So in that way, see here, it's not comparing A1 with A0. No, it's not comparing A1 with B1. No, it's not comparing A0 with B0. No, it's on the whole comparing A with B. So this whole A is nothing but A1, A0, and B is your B1, B0. Okay. So equal to, greater than, lesser than B. So these were discussed in our last class, and we got these equations, right? And any of you, did you use your K-maps and verify if these equations were correct? Remember in the last class I had told to use K-maps and check if these equations are correct. Any of you have done it?
So the third one I've got, like for the condition
Less than.
A less than B.
Okay, so one condition you have checked. Good, good. Similarly, you can check for equal to and greater than also. See, the reason why I'm asking you students to get this is because this will revise your concepts on the K-map. This will revise your concepts on, how to, fill your K-maps, okay, and how your truth table is obtained. See, human mind is in such a way that, if you just see and you leave it, you tend to remember only for a short period of time. But when you see, you understand, and you write it, and when you practice, okay, that's when the retention level is high. I want you all to do that, okay, so that it becomes easier for your internals, for your semester end examinations, okay. You don't have to practice at that time. At that time, you can just glance your sheets, okay. So that's my, advice to all of you. Then and there, whenever the class happens, okay, just make sure that you listen to the class properly. If any doubts, I'm always there with you, right? You can clarify the doubts, and make sure that whatever simple assignments are given, okay. So see, for example, I told you to verify this, right? This is a simple thing. It might hardly take even 5 minutes, right? You already have the truth table here. I have sent my notes, right? For cross verifying, you have the equation here. So it's going to practice, and you're going to even have a look at the grouping of ones, right? You can do it on your own, right? So that's the reason I told you to have a check on this equation. So by next class, okay, I want all of you to verify if these equations are correct or not. Individually, I will ask, okay, I will ask, and I will tell you to turn on your video and show the working of this K-map. Is that clear, students?
Yes, sir.
Thank you. So for today's discussion, let's continue about the code conversion. Okay, so normally when I say a code, which means it's going to be something different than the normal, right? Something different than the normal. So in previous days, okay, in the times of war, okay, World War, so people were a little scared to speak in the normal language. So what happened was there were a lot of coding algorithms that came up, okay, during World War I and II, where they wanted to actually transmit message, and then the listener, okay, someone who is listening in between, who is not supposed to, should not be able to understand as to what communication was sent, okay. So these code converters also are a type of that sort, okay, which helps us in conveying the message, but adding certain code. So it's just like a lock and a key. So key will correspond to a particular lock. If I use a different key for the same lock, then it's not going to work out, right? Okay. The availability of large variety of codes for the same discrete elements of information results in the use of different codes by different digital systems. It is sometimes necessary to use the output of one system as the input to the other. Systems are always connected, okay, one after the other. The output of first stage is dependent on the second stage. Okay, so the output of first stage becomes the input to the next stage, or the output of nth stage, okay, is actually given to another stage, right? A conversion circuit must be inserted between two systems if each uses different codes for the same information. So we just have a certain information, and this key, okay, key is in the form of circuit, should be inserted in between so that a normal conversion is going to happen. Say, for example, instead of letter A, if I use C, what is the code? It is alphabet plus 2, right? Whatever alphabet, suppose I say A, P, P, L, E, and I code it with plus 2 alphabets, then it gives me another code, right? So if I want to decode this, and then I'll have to minus 2 with that, minus 2 alphabets, right? So input is going to be your BCD, okay, which is your binary coded decimal, okay, which is actually from 0 to 9, okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 to 9. And the output is XS3. As the word suggests, XS3. Okay, whatever is the value, I'm adding 3 to it. So here I have 0, 0 plus 3 is nothing but 3. Okay, to whatever value you have here, you are adding 3. Right. Okay, so now let us take another one here. I have 1. Okay, this whole value, I have 1. So to this, I'll be adding plus 3. So once I add plus 3, I should be getting how much? 4. So 0, 1, 0, 0 is nothing but my 4. Similarly, take 9. Okay, take 9 here. So 9 plus 3 is how much? 12, right? So 8 plus 4. So this is nothing but my 12. Okay, so students, are you clear with this truth table as to how we have got it?
No, sir.
Sir, I had one doubt, sir.
Sorry?
Sir, I
Yes,
had one
yes,
doubt.
yes, yes. Go ahead, go ahead.
Sir, in the input part, the last value that we have given for ABCD is 1001, which is not like the last input actually, because it would have been 1111. Sir, is it because that excess input does not exist?
See, a reason why we have done it is because your numbers. Now, look at your numbers, your decimal numbers. Actually, frankly speaking, your numbers are only between from 0 to 9, right? After that, any number that you take, it's on the repetition. 10 is what? A combination of 1 and 0, which you have already included in the set of 0 to 9, isn't it? So 0 to 9 is the main set. Okay. And using 0 to 9, I can generate any number. Understood?
Yes, sir.
Yeah, decimal means how much? 10 values. So 0 to 9 is how much? 10 values. Okay, deci means 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So decimal means 10. So I have totally 10 values here, total. Okay. So to this, we are actually adding. I think some of you still have doubt as to how this is done, right? Okay. So let us take this as an example. Let us say my input is 0, 1, 0, 0. So how much is it here actually? It is 4, right? So 4 plus 3 is how much? 4 plus 3, I should get how much? I should get
7.
Yeah. So this is my 70. How is it 7? How is it 7? 4. Okay. 2, 1. Is that clear, students? So this is how I'm going to generate my input and output. Okay. Any doubts as to how we got this truth table? Very simple, right? Any doubts, students? You can ask me. I can explain it again.
Sir, could you explain it once more, sir?
Yeah. Now let us take the first value here. Okay, what is the first value? 0. What we are supposed to do? We are supposed to generate a code called XS3. XS3, XS means what? More. And by how much is it more? By the number 3. Okay, so which means whatever value I have here towards my LHS, okay, which is my input column, I am adding 3 to it. So here my value is how much? 0. So I will add 3 to this value. So 0 plus 3 is how much? 0 plus 3 is how much? Students, respond. How much is 0 plus 3? The normal normal addition, 3, right? So isn't this 3 here? This is 3, right? So you have 2 and you have 1. 2 plus 1, 3. Right? So let us take one more, 7, 10. Yeah. So we will take this one as example. So I have 7 here. Okay, 111 is what? 7. Okay, so 7 plus 3 should give me 10. So here I get 8, right? And here I get 2. So 8 plus 2 is 10. Okay, so here 7 and excess 3. So 7 plus 3. So which is nothing but 10. So this 10 is what I am getting here. That addition is what I am getting here. So students, is it clear?
Yes, sir.
Yes?
Yes, sir.
Okay, fine. So we'll move on and we will see how we can use this truth table. So as you all know, first, our main idea is to actually generate the truth table. Once we have the truth table, okay, we either use K-map or we use something called Quinn-McCluskey. Of course, it's not for your syllabus, but then it is like your MEV method and K-map. It's one of the reduction techniques. Okay, so this one can actually be put up in your K-map, and you can generate your equations. So now what I want you to do is put this W in your K-map. Okay, put this X in your K-map, put the Y in your K-map, and put the Z in your K-map. You are going to get certain equations. So can you all quickly do that? I will give you a quick 5 minutes. Please do not refer to my notes. Okay, and try to take this as a practice and tell me if you're getting the right equation. So for W, you will have to generate an equation. For X, an equation. For Y is equal to something. For Z is equal to something. So how will you do that? You have A, B, C, D here. Okay, put those values into your K-map and do the reduction. Okay, just for your reference, I'm showing here you have 0, 0, 0, 1, 1, 1, 1, 0. Similarly, 0, 0, 0, 1, 1, 1, 1, 0. So you can take ones and you can actually find out the values. Okay, so can someone tell me what is the equation for W? Do not refer to my notes, just practice it, write it on your sheet and tell me what is the equation for W.
Sir?
The equation that you told, is it for W?
Yes, sir.
You'll have to look it out again. Just check. Just check. Okay, we will continue our discussion and I will explain how we are doing it. So right now I think all of you have started working out. Okay, and some of you have given your answers, which is good. Fine. So we have the truth table here, W, X, Y, Z, right? So individually, what we will do is first we will take Z. Okay, anything you can take. Okay, for that matter. So right. So one of your friend asked me the question, sir, how do we know that we have to take don't care? Now the value that you have here is only till 9, right? So after 9, you have few more 9, 10, 11, 12, 13, 14, okay, till your highest value, right? Till your triple one. So all that you make don't care. Okay. For rest of the things you have your values, right? So for what am I making? See, till 9 I have. Okay. So I hope you can see my screen clearly, right? So 10, 11, 12, 13, 14, 15, all these values I do not have. So what I will do, I will just put it as don't care. So don't care can either become 0 or it can become 1. So I will use it for my benefit. Understood? Understood. So what is my benefit here? What is my benefit here? When I said I will use it for my benefit, what is my benefit here? To have
Grouping,
what?
sir.
Yes, to have grouping, to have more number of ones. Okay, good. So in that fashion, okay, I will get my group here, okay, which means I will get 1, 2, 3, 4. I'll get a octet here. So 8 8 boxes, 8 squares I can actually group. So once this is done, okay, what is going to happen? You have 0, 0, 0, 1, 1, 1, 1, 0. Totally it's going to get cancelled out. So I have to now look at only 0, 0 and 1, 0. So which is common here? D bar, low D. So Z is equal to D bar. Right? So you understood, students? You understood how we are taking? So the K map remains the same for everything. Okay, wherever we have don't care, see, wherever we have don't care, I have not written the value of the squares in the next maps here. Okay, I have just done the don't care and I have inserted the values. Okay, whatever was the values here in our truth table, right? In our truth table, so the same values are actually put up here. So students, any doubts here as to how we got this equation W, X, Y, and Z?
Sir,
Any
can we
doubt?
solve without putting the don't care? Without putting the don't care terms, can we solve it?
It becomes difficult, Sayan. You know why? See, because see now if you just take this 2 ones as a group, okay, here you will take only 2 ones. So I'll have 1, 2, second group, okay, or I can even take 4 ones here. Okay, then this single one will be remaining as it is. So which means my equation is not going to be optimized, right? The more number of grouping, okay, if there are more ones or zeros in a group, then what is going to happen? I'm going to get a simple equation. See, Z is just equal to D bar. Okay, so now if you see here, try to compare, let me just annotate. I will now backtrace. Okay, I will now backtrace and make you understand as to how this works. Now, sorry about that. Now I want you to concentrate on only this D, okay, and I want you to concentrate on Z. So basically, what is a truth table? A truth table is nothing but giving a relationship between input and output, right? So what equation we got? Z is equal to D bar. Now try to compare. Okay, try to compare them and you will understand. So D is 0. What is Z here? 1, right? So let's take another case. D is 0 here. What is Z? 1. Okay. Let's take one more case. D is 0 here. What is Z here? 1. So exactly what's happening? my Z is equal to D bar. So whatever is the value of D, the reverse is happening to Z. So Cyan, if you don't take more number of ones, okay, what by that I mean, if you don't take a larger group, okay, then we are not going to get a simple equation. Okay, less number of group, less number of ones, then your equation is going to become more complex. So which means it's not optimized. Understood? So that's the reason that we are taking water.
Don't care terms.
Exactly. So if I take don't care terms, then I can actually use them for my benefit. How am I using them? I will just make it a bigger group here, a bigger group here, simple. So I get 8 ones together. So this don't care, what am I doing here? I'm treating it as 1. This don't care also, I'm treating it as 1. So it is serving my purpose, right? So similarly, you can work out with Z, W, X, Y, all these equations. Right. So once we have these equations, okay, then you can summarize them, okay, and you can put it here. So what do we do once we have the equations? Tell me.
Logic diagram.
Yes, we can use a logic diagram. Once you have the logical diagram, you can even convert it to a universal diagram using NAND gate or NOR gate, using the bubbling method that I discussed with all of you. So all these, are here. So Z is equal to D bar. So D is here, A, B, C, D are my inputs, right? W, X, Y, Z are my outputs. So look at your truth table here. A, B, C, D is your input, W, X, Y, Z is your output, right? Okay. So I will have ABCD here. So D, I put an inverter, D bar, Z is equal to D bar, right? And now let us see another one. Y is equal to CD plus C bar, D bar, right? So Y is equal to CD plus, and then I convert them, okay, C bar plus D bar, okay. So this is my optimized equation. Okay, this is De Morgan's theorem. I used De Morgan's theorem here. So I put a bar, and then I converted multiplication to addition and took a whole bar. So there is a lot of things, that you guys can do with respect to Boolean algebra, techniques, K-maps, right? It's all about passion. It's all about attention to detail. It's all about how much interest you have in getting your equation as simple as possible. So the simpler the equation, the better is going to be your circuit. Why is it better? Because the number of gates are going to reduce. If the number of gates are reducing, which means less space I'm going to take up on my printed circuit board. So if it is less space, which means it's going to be smaller but performing the same function, right? So next was your NAND and NOR implementation. Of course, we have discussed these concepts in my previous classes. Okay, so we are left out with one more topic, which is MUX implementation. Okay, so we will be doing that in the next session. I'll be giving in your attendance link. You all can give in your attendance now. So this is going to be your last topic, okay, in the second module, which is MUX using pass gates and inverters. Okay, and we will be discussing about the realization of different logics using 2:1 multiplexer. Okay, so different logics can be implemented using your MUX, as I told you in the previous classes, right? Any logic with your multiplexer. So you have the set of inputs and a output. So the first thing that we will look is MUX using pass gates and inverters. So you should understand what is a MUX. Okay, this is the symbol of your MUX. Okay, where you have A, B as your inputs. Okay, and this is a 2:1 MUX. Why is it called a 2:1 MUX? Because students, can you respond? Why is it called 2:1 MUX?
Because it has two inputs and one output.
Good, good. Thank you. So our inputs are A and B, and we have a single output. And by the way, what is C here? C is also a kind of input, right? What is it?
Clock, sir.
Select, right? It's select line. So this will determine as to which input is actually passing and coming across my output, right? So that becomes your select line. Some of the authors refer to it as control signal. Okay, so it's fine. So get used to different terms used for the same functionality. This gate selects either input A or B based on the value of your select line or your control signal. When C is logic low, when C is equal to 0, then A comes out as the output. If C is equal to 1, okay, then what happens? B comes out as your output. So this is a simple explanation or simple representation of your 2:1 MUX. If a question is asked, what is MUX, then you can see a MUX is a digital device which has multiple inputs but a single output. DMUX, okay, on the other hand, is reverse. Okay, it's the reverse of this. So your pass transistor logic leads to efficient multiplexers. Multiplexing is different from basic Boolean function when we are dealing with AND or NOT, etc. We're using a logic gate to implement a logic function. Right? So this is about your pass transistors. So which means I'm using just basic gates to implement any Boolean function. But here, this is not like your implementation of Boolean function, but this is your MUX. Multiplexing, on the other hand, is more like switching functionality that can be implemented using logic gates because they are readily available and they get the job done. So instead of using my basic gates, okay, and or not, instead of using them, I can even make the use of MUX. And once I have the MUX, I can implement any function, okay, and these are readily available, which means they are manufactured, and I don't have to combine AND gate or gate, okay, make a complex circuit, connect wires between them. No, I can just use a MUX, and using MUX I can program it and make it work like any other logical circuit. They do indeed get the job done, but not very efficiently. Now this is a downside. Comfort and efficiency. In other words, comfort and performance do not go hand in hand. It can be anything for that matter. It can be in your life, it can be in the subject, okay, it can be in the concepts that we are discussing. Anything that is comfortable is not going to be efficient. So which means when a homework is given, you should always practice. So if you practice, what is going to happen? You're going to learn as to what mistakes you are doing, where you have to understand. So that gets, you know, understood, and you can retain more things in your brain. The gate configuration shown below seems rather awkward for a task as simple as selecting between one or two input signals, especially when you consider that each inverter-based AND gate or gate requires 6 transistors. So we will see what this statement is telling us. Okay, now this is a standard 2:1 CMOS multiplexer. Okay, now how did I come up with this equation here? How did I come up with this function here? How did I come up with this gate here? Can someone tell me? How did I get this? How did I get it? Remember, we had discussed about our gates where I1 is equal to your A bar, B bar, right? 0, 0, 0, 1, 1, 0, 1, 1. The same concept here. Okay. So S is low, which means S bar and A. Okay. So when S is high, then I'm going to get B. So what is this S here? This S is nothing but your select line or your control signal, which is C. The control signal, which is C. Okay, so instead of C, I have used S there. Okay, so when S is low, I am getting A. When S is high, I am getting B. So both are multiplied and added. Okay. Fine. A multiplexer or MUX is a combinational circuit that selects several analog or digital input signals and forwards the selected input into a single output line. Okay, so that's the function of a MUX. It will have multiple inputs and it will have a single output. A multiplexer, now this is important, make note of this. A multiplexer of 2 raised to n inputs has n select lines. Okay, now say for example, I am having two single input, I'm having A and B as input. Okay, so I'm going to have a single select line. So as our number of inputs increase, okay, the select lines also does increase. So it is dependent on 2 raised to n. So the power of n is going to be a select lines. Now look at this functionality here. Okay, I have two inputs A and B, okay, and my select line, and my output is nothing but Z. Okay, so AB is my input, S is my select line. So you can see here S has two values, S is equal to 0 and S is equal to 1. I have modified this truth table in such a way that it accommodates all the values. So you have AB, which is 0 0 0 1 1 0 1 1. So this is when S is equal to 0 case. Similarly, when S is equal to 1 also, okay, I will have 0 0 0 1 1 0 1 1. Now what is my output going to be when S is equal to 0? It's going to be 0. Okay, then for this combination it's going to be 0. Next, why is it 0? Because A is coming through, right? Whatever is the value of A, so that A is coming to my Z. Similarly, A is 0, Z is also 0. A is 1, Z is 1, A is 1, Z is 1. So Z is following, output is following input A. Now let's see the other case. In the other case, B, when my select line is 1, okay, S is equal to 1, then B comes across my output. Select is 1, so you see 0 1 0 1 0 1 0 1. So this is how we are going to generate the truth table. Once I have the truth table, as I told you, my Z is equal to, I will need 2 AND gates and 1 OR gate to implement it. Okay, so this is nothing but A into S bar, because when S is equal to 0, I'm getting A plus B into S. Okay, because when S is equal to high, I am getting B as my output. So both are getting odd. So students, any doubt still here as to how we have got this, how we got the truth table, and how we got this particular logical diagram? Any doubts here, students?
No, sir.
Okay, fine. That's good. So we have this equation, truth table, representation, logical diagram. Okay, fine. Now look at this diagram. Okay, I'm going to slightly increase the complexity. Now instead of 2:1, I'm going to use a 4:1 MUX. We have seen this already, right? We have seen this in our initial classes as to how I use 2:1 MUX, combine them and give them to another output here, which is Z. So my AC BD is here, okay, and then I have my select lines S0. Okay, S0 is common to both the first MUX, second MUX, and S1. When S1 is high, then it's going to take outputs from stage 1. So this is my stage 1. This is my stage 2 MUX. So when S is high, these are enabled. Okay, it starts taking my values, because when I don't enable this select line, what is going to happen? It's not going to take 0, nor it's going to take 1. So which means this whole MUX is it's in non-working mode. So fine. So whenever I select the value when S0 and S1 0 0, A is going to come. Okay, 0 0, then A is actually going to come across my output Z. So similarly here, this is 0, 1, and this is 1, 0, and this is 1, 1, because it is ABCD, right? So bar is 0, 0, bar is 0, 1, 1, 0, 1, 1. So this is the easy way of remembering and writing the equation. Okay, so you have your MUX here, you have your equation here. So we have used 2:1 MUX. Now I might ask you a question. Design a pass transistor, okay, using 2:1 MUX. So what is a pass transistor? As the name suggests, it just passes the value. Okay, it just passes the value from its input to output side. So that's the functionality of a MUX, right? Whatever is at your input, the same thing gets propagated and sits across your output line. So this is the same thing here, right? What we have used here is your NMOS, okay, N type of transistor, okay, because there's no bubble, right? So this is the N type of transistor. A multiplexer can be designed using various logics. Okay, so this figure shows how a 2:1 MUX is implemented using pass transistor logic. So either I can use only NMOS, okay, or I can use PMOS. But remember, your NMOS is good for passing zeros and your PMOS is good for passing ones. So here, normally in our practice, we use N type of transistors more than P type of transistors. Does anyone know the reason for that, as to why we use extensively N type of transistors than P type? Yes. Okay, so I want you to find out answer for that, and we will discuss that in the next class. Okay, right. So I have A as my input here, so source, gate, and drain. Source, gate, and drain. Okay, we have a message. N has majority charge carriers as electrons. Okay, so if it's electrons, then what next? Okay, you're almost there.
Sir, is it because N channel will always indicate a higher voltage, like when it is working? So that's why we may be using N channel more often.
That's because N type means majority is what? Electrons, right? Electrons are much faster than holes. Okay, they are lighter than holes. So if they are lighter, they can propagate fast. So that's the reason we use N type of transistors, because the majority carriers are N type. N type means electrons. Electrons means less dense. Less dense means fast. So I want something which works out fast. Understood?
Yes, sir.
Okay. So here I have to pass my value A, okay, and I have to pass my value B. So using these transistors, if my gate is open, then only this value will pass. If my gate is open, then only my value will pass. So normally when it's in series, what we do is we multiply them, right? So A into S bar, okay, and these two are what? In parallel, B into S. So parallel becomes plus. Okay, remember my NMOS at the right hand side I had written, if they are in series they are multiplying, and if they are in parallel they add, right? So these two are parallel. Okay, so addition comes here, and here the value passes, so A into S bar, B into S, so A into S bar plus B into S. So this is how you implement your pass transistor logic. In the upcoming classes, okay, we will see a few more concepts as to how I design a 4:1 pass transistor logic. All these things we will see in the upcoming classes. Okay.